Now next, I'm going to call on stage Dr. Goutam Paul. Goutam completed his bachelor degree in computer engineering from IIEST Shibpur, which is another renowned institute of this country from this region. He did his master degree in computer science from State University of New York at Albany, U.S.A, and Ph.D. in cryptology from Indian Statistical Institute. From 2006 to 13, he was an assistant professor in the Department of Computer Science and Engineering of Jadavpur University, Kolkata, India. Currently, Dr. Paul is serving as an associate professor at Cryptology and Security Research Unit of Indian Statistical Institute, Kolkata. Dr. Paul received the prestigious Alexander von Humboldt Award of Germany in 2012 and the Young Scientist Award from the National Academy of Sciences, India in 2013. Dr. Paul's research area is classical and quantum cryptography. He is known for his cryptanalysis in RC4 of IEEE WiFi protocol. Welcome, Dr. Goutam Paul.
Thank you for the introduction. I think I'm the last speaker, so second last, okay, almost. So it's almost the end of the day. So I try to be brief and to the point, and try to cut down on the heavy mathematics stuff. Okay, try to get into the main idea of the story. So as you see, the talk is about IEEE WiFi and TLS Cipher suite. One is data link layer protocol, the other one is application layer protocol. So it's this brief. One is NAT and physical layer, and the other is application layer. IEEE 802.11, you know that it's WLAN standard, right? Mostly used for domestic and office network. And these are the common usage: A, B, G, N, AC, AD, and I think now AX people are talking about, right? And Wi-Fi. Especially most of the Wi-Fi protocol fall in this 11B part. Okay. So in that Wi-Fi Alliance has actually renamed this Cipher suite as Wi-Fi generation 1 to 6, so that it's easy to identify. 11B is generation 1, A is generation 2, and so forth. It's there. Right. Now, among these Wi-Fi protocol, the very first one that was commercially popular was web. Web is word equivalent privacy. So the idea was that in the wireless domain, actually you have less security because the signal everyone gets access to very easily, right? And also there are multiple recipients for the same signal. Whereas in the LAN, in the word LAN, you have the fixed recipients, right? Depending on the routing, depending on the cabling, you have fixed set of recipients. But here in the wireless domain, anybody can tap into the signal. So there you have to be more careful about the security. So therefore the name given on this protocol was word equivalent privacy, because the expectation was that it will give you the same feeling of security as if you are using the word. Right? So that was the web protocol about. And inside it used to use 24-bit IV. So IV I will explain for those who are not familiar with the term. So basically what happens in any crypto system, there is a secret key, right? And assuming a symmetric key system, but the sender and the receiver use the same secret key. Then every time the sender encrypts a message with the same secret key, the receiver will be able to decrypt it with the same secret key, right? Now suppose the sender happens to send two messages which are same. It may happen. There may be two senders using the communication network, and maybe they are using the same message, right? Some common message may happen very frequently. Some hologram or something. Now, if it is the same secret key, if it is the same message, and you are using the same algorithm, because everything is deterministic, ultimately the ciphertext will also be the same. Now, these repetitions in the ciphertext will be some kind of information leakage to the attacker. The basic information is you are sending the same plain text. That is one. Then you can manipulate, you can form XOR, the difference of the two, and then find out some information about the data depending on the algorithm. So what this IV does, it's called initialization vector, is that every time when you use a new session, let's say every time you close the browser and you open the browser, it's assigned a new IV, which is, you can think of it as a session ID, right? So that is mixed with the secret key to form what is called a session key, right? And this session key goes into the encryption algorithm. So effectively, though the secret key remains the same over multiple sessions, but in every session, effectively you are having a different key because it's getting mixed with the session ID, with the session number or the IV, which is called initialization vector. So in this protocol, they use 24-bit IP and then 40-bit secret key. So 64-bit, nowadays it's very poor, but that time 64-bit was good enough. Right? So that was RC4 session. And also an extended 128-bit web protocol was also available, and that was also broken subsequently. I'll come to that. Okay. Then the next generation of this wireless encryption was WPA, wireless protected access, that was web advanced, I would say. That's part of 802.11i, successor to web. And they use something called temporal key integrity protocol. So basically it's nothing but more sophisticated key mixing. So in web, the key mixing was nothing but concatenation, right? So you had the IV or the session number and the common secret. So together they form the session key, right, which will go into the encryption. But that was very preliminary level of key mixing, right? So the attacker knows that, okay, the first 3 bytes are actually the IV, the next bytes are key, so on and so forth. Whereas in WPA, the next version of web, you mix it with complicated mixing algorithm, right? So you do some substitution, some permutation, some data movement here and there, do some mathematical operation, and at the end of the it, you get a good mixture. So from the mixture, it is difficult to now get back the actual secret key and the IV by an attacker who has no other information. So that's the difference of web and WPA. And that is actually WPA1. So if you use your laptop or mobile in any WLAN, you will see that you go to the security tab, right? It will ask you that which level of security you want, right? Whether it's web 1 or web 2. So web 1 was actually using RC4, but because of its weaknesses that I will talk about shortly, it has been replaced by WPA2. WPA1 has been replaced by WPA2, and it uses an AES-based encryption, which is supposed to be a little more secure. Right? Then let's come to TLS. You know that it's a successor of SSL, right? An application layer protocol, and web browser, email, instant messaging, VoIP, all of them use TLS. The security of TLS, so there are 3 aspects of security here. First level, that you have to ensure the privacy, that means the data that is being transmitted between the sender and the receiver, right? So that will be ensured by symmetric cryptography. And the second level of security is identifying the source and the receiver. So that will be done using public key cryptography, using any identity algorithm. And the third level is message integrity, that means the data that is being transmitted over the channel that has not been tampered with or that has not been subjected to some noise, right? There might be some error in the data. So to prevent data loss and alteration of the data. So these 3 different algorithm suits are required to meet the security criteria in TLS, and as a matter of fact, any such communication protocol, right? So this is the authentication and encryption algorithm list. So we have key exchange by typical RSA, Diffie-Hellman, elliptic curve Diffie-Hellman, etc. Then the block ciphers and stream ciphers, they are used for encryption, right? The block cipher is AES, Galois counter mode, common counter mode, Camellia, ASC, etc. RC2 is Ron's code developed by Ron Rivest, who is also the co-inventor of RC4. But RC2 is it's a series of cipher developed by Ron, right? RC1, RC2, RC6, up to that much, and RC2 is a block cipher, RC4 is a stream cipher. And we all know that was part of SL2 and in 3, but TLS 1.2 it was part, but in 1.3 it was actually removed. So in TLS 1.2 and 3, this Cha-Cha-Cha 20 has been introduced as a replacement of RC4. So, and this HMAC typically is the data integrity algorithm, the hash function, right, to ensure data integrity. So, the rest of the talk will talk about this story of this replacement of RC4 by Chacha, the technical story, why it happened, and what are the internal problems of RC4. Look into it. So, the data structure of RC4 is very simple. It's an array. So, all of you know how to use array in any programming language, right? So, it's an array. You can think of n here as 256. So, every position is actually 1 byte here. So, you have 256 bytes, n bytes. Right? So, now you have the secret key. This is L. Now, L can be your choice. So, typically you have 128-bit secret key, right? So, that is 16 byte. So, you can take L as 16. So, these are just parameters. So, then you have this expanded key. This is nothing to allow, to align the secret key along with this S. S kind of you can think of as the internal state, right? You all know about the stateless protocol and stateful protocol. So, for TCP/IP stuff like that. So, similarly, in this encryption algorithm, you can think of that the algorithm is going through multiple states, and this S array is nothing but the state of the algorithm, right? It contains the state. So, fine. So, the state size to make the key length equal to the state length, because state length is typically 256, as I was telling you, the key length is typically 16. To make them equal, the key is actually repeated at key length boundary. So, to make it the expanded key of the same length as the state. More state. So, the next is, we have two index I and j to access the array elements. I is incremented deterministically, j is incremented randomly, and we have a swap between the two indices. That's the main algorithm. So, we will come to it, and all additions will be modulo n, because of the simple fact that when you are adding two indices, right, you should not have array index out of bound exception. So, if you are adding two indices, the indices value are between 0 to 255, because they have 256 element, but when you add them, it can go beyond 256. So, to wrap it around within the limit 0 to 255, we are just doing modulo 256 addition, as simple as that. Right. So, RC4 key scheduling algorithm. So, it has two components, the key scheduling and the pseudo-random generation algorithm. So, just remember the S array, the state. So, all we are showing is the RC4 state, the S array. So, initially we initialize the state to be the identity. Identity means every index position we have the same value as the index. So, S0 has the value 0, right? S0 has the value 0, S1 has the value 1, S255 has the value 255. So, that's the simple initialization. Very easy to do. And next, you increment I deterministically, this for loop does that, I0 to 255. And then j is incremented pseudo-randomly. How? By adding the current value of j, which is initialized to 0, by the current state byte, and you add the current extended key byte. As simple as that. They are all pointed by I, and then you swap. So, it's a 3-line algorithm, as you can see. So, what it does, so basically you run it over each entry. So, you access each entry and swap it with a random entry in the same way. That's basically what you are doing here. And at the end of that, initially the state was an identity, because every index has the same value. After the end of this, the state will be scrambled. So, what you are doing, you are using the randomness of the secret key to introduce randomness into the state. The state was initially non-random. Professor Roy was talking about randomness and non-randomness, right? How we can distinguish between them. So, here it comes that initially the state was completely non-random. You can predict in this index I have this value, but after this operation, this key scheduling operation, basically the state is having the same values, but in a random permutation, right? Some value are going to the left, some value are going to the right. So, from an index we cannot guess its value. So, now the next part of the algorithm does not use secret key at all. So, whatever randomness was in the secret key, what that has been embedded into the state now. Now, this scrambled state will be used in the next phase for the actual encryption. So, that is called the pseudo-random generation algorithm. So this is also pretty much similar to the previous algorithm. You initialize the counters I and j. You have two counters because you have to swap. And again you increment I deterministically and j pseudo-randomly. Why pseudo-randomly? Because you are adding the SI. Now SI is now random, right? Because it is transient. It is no longer identity. Previously SI was I in the previous slide. Now there you had plus ki. Here you don't have ki. So you swap SI and Sj, then this output SI and Sj together, you add modulo 2. So the addition will give you an index, and that index is coming here. So you are taking SI, you are taking Sj, this is addition. This addition will be another index once you wrap it around, and from that index you get the output byte, current output byte. So as simple as that. Now you can XOR this output byte, it's a stream cipher with the plain text. So that's the simple RC4 encryption. Now, so this is a toy example. I'm skipping it, you can go through it, very simple. So the key, sample state, it's a reduced version, 8, n is 8 instead of 256. Now initially S is identity, as you can see, 0 to 7. So after I is 0, following the algorithm j becomes 3, so you swap the 0 and the 3 location, so you get this, 0 goes here and 3 comes here. So this is the state after first step. Next step, I is deterministically incremented here, you can see 0 to 7, and j is si plus sj plus ki. If you do the next step, j is 5, so that means 1 and 5, that rotation will be swapped. So this 1 and 5, 3, 4, 5, right? So 5 comes here and 1 comes here. So this is the next step, and so on. Very simple. Right. So similarly, PRJ you can follow, and these are actually the key stream bytes, this is the output byte. So these will be XORed, bitwise XORed with the message bytes to give you the encryption. Fine. So the wave attack model. So how the wave attack produced? The idea was as follows. So recall that in wave we had a very simple key mixing process. Right? So of course the other attacks are very complicated. So I will focus on the wave attack just to show you that how actually this type of cryptanalysis is being done, and some other example also. So this initial vector, the session ID, right, which is the initial x bytes. So that is k0 to kl minus 1 minus x. And the next is key bytes, you can see here. So as if this ID and then the concatenation, these key bytes, and together that is the secret. So k0 to l minus 1. So essentially, all the wave attacks that are known, that are based on some event A. So basically we are doing a statistical testing, whether an event occurs or not, and nothing else. So what is the event? The event actually relates one unknown key byte or maybe a sum of key bytes, because you are adding the keys in multiple rounds, with known IV bytes, because these IVs are known, the session IDs are known, right? IVs are known, that can be easily known. So to relate this unknown portion with the known portion, right? Some relationship between them, that is the event. If the relation holds, the event is true, otherwise it is false. And we apply probability on top of that, and then it's a statistical analysis, right? So if the probability of such an event is greater than 1 by n, so usually the left hand side is a combination of bytes, the right hand side is a combination of bytes, so it's essentially two random bytes being equal, so the probability should be 1 by 256 or 1 by n. However, if it is greater than 1 by n, then we call it's a bias successful attack. But statistically, if it is less than 1 by n, also we have an attack, but practically here in this protocol, it turns out that we have greater than 1 by n, right? So what is important is how many sessions you need to actually mount that, right? So the attacker's goal would be less number of sessions to mount the attack, then the attack is more efficient, right? You need less amount of data to crunch. So that will depend on how strong this bias is, okay, in any protocol. So these are generic things. So any algorithm in any protocol, if you want to break, you have the efficiency of the attack will be measured by the data that you want to use and the time that you will be using. Of course, more data you need more time, but they are not always exactly proportional, but they are related, of course. So here we are measuring data complexity or the session number of sessions. So that will depend on how strong this bias is, how further away from 1 by n this probability is, right? And all the wave models, attack models that actually follow this. So So I chose to describe this part because that is actually the foundation of all the web attacks instead of going into each and every attack in detail. So now we can summarize this. So if you know this probability P, right, using this Shannon's notion that Vijan was talking about, we can formulate the number of sessions needed using this formula. Okay, number of sessions needed to mount the attack. Now you can see here that more is the bias, the higher is the P, right? The less number, because the numerator is constant, the denominator will go up, you have less number of sessions. So web attack variants, so summary of the attacks, I have given a description of the event, there is no need to go through them in detail, you just look into the probability, right? So this is probability of this attack, now this is slightly more, so they need less data. So initially we need 6 million packets for this probability, but as soon as the probability is 1.1 by 256, we need 2 to the power 25 packets. And here success probability also increases. That means success probability means if you mount the same attack 100 times, how many times you are going to get the secret key. Okay. So similarly, here you see 1.36 is slightly higher probability. The events are different. So this is based on a different event, this is based on a different event, but all the events are relating unknown key bytes with some known IP bytes or statements. So that is the basic principle. Okay. So more probability and less data, 43,000 packets, and so on. So this is the basic idea. Okay. You see that it's increasing. So now from web and WPA, we will go into some other mode of attack. For the rest of the talk. This is called biased second output. It's a very famous result discovered by Mankin and Shamir. They discovered that the second output byte of RC4 has a higher probability, not only slightly higher, but actually twice as much probability as the random byte should be. So Z2 is the second byte, second output byte, right? So if you encrypt, it will affect the second message byte. So if you have many bytes in your message to encrypt, the second byte will be affected by the second output because it will be XOR with this, right? Now every output byte should take every value between 0 to 255 with equal probability. That means 1 by 256. Every byte value should be equally occurring as every output position. So if you fix the output position, if I repeat the experiment multiple times, sometimes the second byte will be 1, sometimes the second byte will be 135, sometimes it will be 255, sometimes it will be 0. So if I run it many times, the same algorithm, the second output byte should be coming 0 equally as any other number, and uniform value is 1 by 256. But it turns out that the byte 0 occurs with twice as much probability as the randomness. So that's a huge bias, and based on that, they mount an attack on broadcast RC4. So the broadcast RC4 is a very simple application. So imagine you have a group email, right? You are sending same email to multiple recipients, or group message, some news group, right? So multicast. So there, because the same message is being sent to multiple recipients, so you are using different secret keys to encrypt, right? So for user 1, you are using secret key 1. For user 2, you are using secret key 2, and so on and so forth. So what you are having that for the same message, you are getting different ciphertexts. Agree? So now let us focus on the second byte of the message, or second byte of the ciphertext, so to say. Now second byte of the message will be XORed with the Z2, which is second byte of the second output of RC4, because every byte will be XORed with the corresponding byte in the output to get the encrypted byte. So second byte of the message will be XORed with the second byte of RC4 to get the second byte of the ciphertext, right? So now you have the same message encrypted via different secret key going to different recipients. So you look into all these different ciphertexts of the same message. Okay, different ciphertexts of the same message going to different recipients. Focus on the second byte of all the ciphertexts. Now they are the encryption of the same second byte of the message. All the second bytes of the different ciphertexts are nothing but different encryptions of the same second byte of the message. Correct? Now the same second byte has been now XORed with different Z2. Different Z2. So since Z2 equal to 0 occurs with twice as much probability, 0 means what? If you XOR, then the same value goes as output. So the message, whatever was the message, XOR with 0 will give you ciphertext, same as the plain text message. So now if you create a frequency table of the second byte of the message, of the ciphertext, then the most frequently occurring value will indicate what was the actual message. So it is the same message byte, different ciphertext byte. You make a table that which value between 0 to 255 occurs how many times in the ciphertext. So you create a frequency table of the different possible values of the ciphertext byte. Of them, the highest occurring value will be the actual message byte. Why? Because there the message has been transferred as it is due to 0, due to this Zord in 0. So that's the simple broadcast attack. Using that attack, any packet of 256 length, let's say the second byte of the packet can be actually easily deciphered in constant time actually. So that's a very strong attack. Now this was done in 2001. Now what we showed in 2011, now there it was fine. The second byte you can decrypt, but what happens to the other byte? If I have a 256 byte message, a 256 byte packet, right? You have many bytes not deciphered for that attack. So what Mantin and Shamir actually claim that this bias is typically the second byte and this bias does not exist in the other bytes, so it cannot be exploited. However, roughly 10 years after this attack, we showed, that was part of my PhD work at that time, that Mantin and Shamir were correct in stating that other bytes do not have the bias, but they do not have the bias of this order. So they are partially wrong. Actually they have the bias, but of a different order. It's not as strong as this bias, but strong enough to break them. So that is actually the next work. Broadcast attack revisited not only the second byte, but actually all the bytes except the first 2 bytes can be actually decrypted. So we show that the bias is of this form of 1 by, so there the bias is 2 by n, the second byte bias. 2 by n you can think of 1 by n plus 1 by n. So the bias is of the order of 1 by n. Here we showed that the bias is of the order of 1 by n plus 1 by n square. So the bias is little less. So you need little more data. That's all to decide that. You need more data samples, more recipients. So you require more recipients of the same message to be able to attack. Nothing else. But actually you can break all the bytes from the third byte to the 255 bytes. Okay, so all the initial 253 bytes can be broken completely. So that was a major attack. And so let's skip this thing. So this is showing the bias. So the bias is initially high, but it decreases, but it still stays above the random value. So this is the perfectly random line, 1 by 256, this black line. Now these are the biases. Now the red one is the theoretical formula that we derived, and the green one is the experimental result, and they roughly match each other. Okay. So this broadcast attack was revisited later by some other people, and they combined some other strong biases to actually further reduce the data requirement. And interestingly, this group by Patterson from Royal Holloway, London, in Usenix 2013, they used our attack of broadcast RC4, but they combined the plain text together. So what we were looking into every byte of the plain text, every byte of the cipher text separately, right? So we were trying to decipher every byte separately. So Patterson's group, what they did, they used our concept, but they tried to look into the probability of multiple bytes together. Okay, try to combine the joint probability of multiple bytes. So that's the extension that they did, and using that they showed that the complexity can be reduced a little further. So that was this attack based on our attack. Next. Yeah. So these are some numbers. Let me skip. These are all basically talking about the probability. You saw that 0.0039 is roughly the 1 by n, 1 by 256 value, the random value, and all these biases you see that are more than 0.0039. And these are some events that I have listed out. So you see these are all combinations of secret key. These are all different combinations of the secret key and they have some bias towards the byte. This is the output byte. So by observing the output byte, actually you can solve some linear equations to get the secret. That's the main idea in this attack that we showed. So that was in 2014. Further improvement using our idea was noise. Should I continue?
Yes.
Fine? Everything's fine? Okay.
Waiting for the agreement.
Yeah. So another significant result that we found is that there are some biases. They depend on the secret key length. So before this work, all the attacks were talking about the bias of the output, the bias in the cipher text, and how to actually decipher the plain text looking into the cipher text. Right. Now here actually we are talking about the dependence of the bias on the secret key length, and we showed that as the key length varies, because you can have 64-byte key, 128, 64-bit key, 128-bit key, 256-bit key, right? You can have different key length. As the key length changes, the bias also changes, right? So you see that this can be used for key length distinguishing. That means if you do not know what is the secret key size that the protocol is using, you can actually use this result to just run a statistical analysis on the cipher data to gauge the secret key perfectly. Right? So we call it key length distinguisher. So this is kind of a unique kind of work, because prior to this work there were no known work in this field about connecting key length with the bias. Right? People are connecting key with the bias, the value of the key with the bias, or the value of the output with the bias, but this was the first work connecting the length with the bias. Okay, then this is an interesting picture. I wanted to show you that all this bias is actually connected to the bias that is introduced in the state after the key scheduling. Okay, so there the algorithm designer have to be careful. So the message is that when you design an algorithm, right, you should, before rolling it out to the market, you should statistically analyze the algorithm so that your state does not have any bias, because if your internal state has some bias, that bias will be reflected in the output. So you see all these biases we are talking about is at the output level. We showed that the algorithm has two components, right? First you scramble the state using secret key. Next you use the state to generate the output in multiple rounds. Now we are observing these biases after the end of the second phase at the output level. But we found out that actually they can be connected. We can erase the second phase and we can look into the scrambled state after the first phase itself, after the key mixing. And that is where all the biases are hidden in the secret state, and they get translated to the biases in the output. Right? So if you look into the state here, state is that array. This, what is the value at S0, what is the value at S1. Right? So ideally what I should expect, so if I draw a 3D plot, right, 3 axes, say in the x axis I draw the index of the array, the state array, 0, 1, 2, 3 to 55, right? And in the y axis, suppose I draw the state value. So every index can have value 0 to 255. Right? So the index 0 to 255, in that index the value can be 0 to 255. So I have x and y axis. So let's say u is the index and v is the value. Right? U runs from 0 to 255, v runs from 0 to 255. Now, what is the value, what is the probability that index u has the value v? what is the probability that index u has value v? So that's a function of both u and v. So that will give you a surface, 3D surface, right? So this is the probability of having the value v at the index u. So it is a two variable function plotted against the parameter u and v, index u and value v. So probability as a function of uv against index u and value v, that ideally should be uniform 1 by n, which is this flat plane shown here. So that shows that for all possible indices and for all possible values, right, it should be 1 by n. Ith index jth value for all I and all j, 256 square many pairs ij should be this flat. But actually, if we plot, and it can be proved also theoretically, that was part of my thesis, that the actual surface looks like this. So you see some negative bias. I was telling you that negative bias will also help. Then you have some positive bias, and then it goes down again, and then it goes up and becomes random. So because of this non-uniformity in the state after the key scheduling, all the biases are being encountered at the output stage, and that are leading to this, broadcast attack, password recovery attack, and attacks of different modes in the TLS 1.2, and so on and so forth. So from algorithm design point of view, I also looked into that how to rescue RC4, and I showed that actually if you keep the same output generating algorithm, but if you only change the key scheduling part, right, how the key is being mixed internally, if you can just add few few extra steps, very less overtake, then actually you can make this distribution close to random. So you can actually flatten this surface, which is the goal. Then you will have less number of bias. So what I am saying is that IETF has recommended that RC4 to be removed from TLS 1.2 to 1.3, but an alternative solution could have been actually to just modify RC4, because it's a lightweight algorithm, it's a popular algorithm, it has been in the commercial domain for many years, and very easy to analyze. That is important because analysis gives you scope of modifications, so on and so forth. So that's just one comment, right? One comment. Okay, so just moving on, there are some recent attacks exploiting RC4. You see that it's called cookie masking. So the Patterson's group have actually extended their work on cookies using RC4. Then another work is on Hive hidden volume encryption system. So that was also using RC4, the disk encryption, how to break that. And then another one is password recovery attack. So you can look into these works. So that uses further applications of our biases altogether. Okay. So with that, I would like to stop. And now we know that RC4 as a scheme cipher has been replaced by Chacha, developed by Dan Bernstein, right? And it's using this poly-hash algorithm for authentication part. And in Chacha also we have looked into for some biases. So we have also found some biases in Chacha. So some cryptanalysis has been done, but they are not practically significant. That means the data requirement is quite high and the time complexity is quite high. So we have some theoretical results in our box on Chacha itself, which is in TLS 1.3, and we are currently continuing further analysis in that direction. Okay. So I'd like to stop and take any questions.
Thank you.
Thank you. Yeah, please.
So as you were discussing, this at the end of the whole session, I think is a kind of culmination point to tell getting at. So engineers are designing protocols, but probably at times scientists should look into the protocols also from a theoretical perspective and from long-term benefit of internet. So probably this is something IDF operations and people involved in IDF should look into this kind of analytical angle of protocol design. And from a very theoretical perspective, of course, engineers will look into the practical implementation. But thank you for this is very interesting and very pertinent because big debate is going on TLS 1.3. Yeah.
And I would like to also add something to that comment, as you rightly said, that always the mathematical security of the algorithm is necessary, but that is not sufficient. It depends how you use it and plug it into the protocol. Like for example, when the transition from web to WPA happened, right? So that time RC4 was considered very secure because these biases were not discovered. So at that point of time, there was no weakness of RC4 algorithm as such. It was just as it was used in the key mixing. How it was, the session IDs were incorporated in the algorithm. So just this ID and the session ID and key mixing layer, that was replaced from web to WPA transition. And then everything was smooth. Only with some other biases, this WPA was also gone. Right? So that's another thing that we have to remember, that not only having a good algorithm, but how you use it and plug it in the protocol, right? Actually, that also has to be done. Please.
Yeah, Nalini, that one thing that we really need for protocol development at the IETF is people such as yourselves to do formal analysis of new cryptographic protocols. And I'll tell you why. Is because anytime like we have a draft going before TLS group or something like that, then the question gets asked, have you done a formal analysis? And I'll tell you something is right now we have Royal Holloway, INRIA, and I'm thinking there may be somebody in Germany. I can count them on the fingers of one hand, the people who can do formal analysis, okay? And so I'm looking at you. I'm looking at you.
So please add Indian Statistical Institute. I would like to be happy to be
my
part of that.
God. Oh my God! Oh my God! Now you guys, I'm telling you, this is my dream come true. I can't tell you how many times we want to do something, but we don't have formal analysis because these people are so busy. And so if we can say, will you guys do a formal analysis of this particular algorithm, and then I will pay your way to come to IETF. I'm telling you. So let's, if
actually, we had some informal discussion with Vijan also that I'd be happy to look into this.
Let's please. Yeah, thank you so much.
Welcome.